This next lecture is on the law of conservation of energy. So we've learned a bit about energy. We learned that energy is the ability to do work. What we're going to learn about here is that energy is a quantity that is conserved throughout the universe. So there's a certain amount of energy, and that energy, whenever we have a loss of energy, there's a gain of energy somewhere else. So we use mechanical energy, which is a combination of kinetic and gravitational potential energy, to do mechanical work every day. But that's not the only type of energy. I alluded to some other types of energy before. This lecture here, we're going to go through those different types of energy. Then we're going to talk about the conservation of energy. Here we have a pot on a stove, and the pot's being heated up. The stove itself runs off electrical energy. That electrical energy is used to heat the coils on the stovetop. Those heated coils then transfer thermal energy to the water inside the pot, and that water inside the pot then cooks the pasta or whatever it is that we're cooking in the water. So those are some examples of energy. We have electrical energy and thermal energy and some interactions between those types of energy. Another type of energy we have is energy from the sun, for example, which is radiant energy. And there's other sources of radiant energy as well. If you have a campfire that causes light, which is really just a type of electromagnetic radiation, but that would be a radiant energy source. A radio tower, for example, would also that radio wave energy is radiant energy. The sun, though, its radiant energy comes from the nuclear fusion reactions that are happening in its core. So there's another type of energy. We have nuclear fusion, which is the fusing of isotopes of hydrogen together into helium. And when that fusing happens, there's a release of energy. And that energy is converted into radiant energy, and the sun ends up lighting itself up in our solar system. We've talked about gravitational potential energy, and we've talked about kinetic energy. There's another type of mechanical type of energy, which would be elastic potential energy. So a trampoline is an example of something that has elastic potential energy. You would also have something like a spring. If you have a spring that's compressed, it has elastic potential energy. A rubber band that is stretched has elastic potential energy as well. Two other types, chemical potential energy. I think in the last lecture I mentioned that in terms of food, but that could also be when we have an interaction between basically two different chemicals or a combination of chemicals. Fireworks would be an example. With fireworks, not only do we have that chemical explosion, but we also have the energy being transmitted through sound. Sound energy is another type of energy. So we didn't mention the word heat because heat is not a form of energy. Heat, when we're talking about physics, heat is the transfer of thermal energy from a warm body to a cooler body. So heat is the transfer of thermal energy. That's how we refer to heat. So heat is a verb in science. It's not a noun. So when you say the hot plate was used to heat the liquid to a temperature of 50 degrees Celsius, we don't say the hot water has more heat than the cold water. The hot water has more thermal energy than the cold water, and the hot plate heated the liquid. So here you can copy down different types of energy. thermal, nuclear, elastic, electrical, gravitational, sound, radiant, chemical, and kinetic. There are other types as well. With nuclear, we can split it up into different types. But these ones, this is just a general kind of list. And also, write down the definition for heat, because later in this unit, after we look at just the conservation of energy, we're going to study two other types of energy. Thermal energy being one, and nuclear energy being another. So this is a question that says name at least one type of energy associated with each of these objects, and I'll let you just kind of go through this. It's maybe try to answer these before you look at the answers, but the first one here says a bonfire roasts a marshmallow, so we have both chemical and radiant energy in that case. The others, you can kind of read these on your own, and we won't spend too much time on them. So when we have a type of energy converting to another type of energy, we call that an energy transformation. So we refer to the example of the stovetop. We have electric energy being converted into thermal energy. There's another example here with a microwave oven. We have the electrical energy converting into radiant energy, which is the microwaves. And that radiant energy, the microwaves, then heat up the food, which is thermal energy. So energy transformation is when we have one transfer or one change of energy to another form. People often wonder how much energy there is in the universe and whether we will eventually run out. And scientists have studied energy and energy transformations and have arrived at some important generalizations. For example, they noticed that when one form of energy is transformed to another, the quantity of one form is reduced by the same amount as the quantity of the other form. So a light bulb might transform 100 joules of electrical energy into 5 joules of radiant energy and 95 joules of thermal energy. However, the total amount of energy has not changed. So this is an example of the conservation of energy. So we've determined that that energy is always conserved. So here, in green, I'd like you to copy down the law of conservation of energy. It is that the total amount of energy in the universe is conserved. There's a certain total amount of energy in the universe. This total never changes. New energy cannot be created out of nothing, and existing energy cannot disappear. The energy that exists can only be changed from one form into another. When an energy transformation occurs, no energy is lost. And here is the law of conservation of energy written in a algebraic way. So the total energy at the start is equal to the total energy during and the total energy at the end. You may also see it written as E subscript I equals E subscript F, which is initial energy equals final energy. So here's an example of the law of conservation of energy. We have a diver jumping into a pool. So at the start of this diver's jump, their mechanical energy is equivalent only to their gravitational potential energy. And in this case, it would be 6.4 kilojoules. At the halfway point, they would have a gravitational potential energy of half of what they had, which is now 3.2. Their kinetic energy would increase from 0 to 3.2 kilojoules. And you can do the calculation for that. It's 1/2 the mass times the velocity squared. And you'd have to find the velocity using our kinematics equations, but that would be, it would work out to 3.2 kilojoules for gravitational, 3.2 kilojoules for kinetic. And here's the calculation here. They find V2, and then they do 1/2 mv2 squared. Notice that the total energy, though, is still the same. It's still 6.4 kilojoules of mechanical energy. And then at the end, just before the water surface, all of that gravitational potential energy is gone. It's all been converted into kinetic energy. And that would work out, I won't go through the calculation with you. You can check it on the slides if you wish. But it works out to be 6.4 kilojoules. Now, all of the mechanical energy is equal to the kinetic energy. So as you can see from these three images, the conservation of energy is the same. The mechanical energy is 6.4 kilojoules throughout. And at any point between the picture 1 on the left and picture 3 on the right, the sum of the Eg plus the Ek will be 6.4 kilojoules. So here's some questions to consider. A ball is dropped vertically from a height of 1.5 meters. It bounces back to a height of 1.3 meters. Does this violate the law of conservation of energy? So it doesn't, because it's not bouncing back to 1.5 or greater. If it did, then that would violate the law of conservation of energy, because you would then have more energy at that point than it did at the start. And also, when we drop a ball, you might think that if it bounces, it should bounce up back to the same height that it was to get back to that Eg it originally had. Although, there are some other things to consider. When the ball hits the ground, it's transferring some other energy as either sound or vibrations into the ground. So there is also a transform of energy every time the ball makes contact with the ground. Here's a question. We have a 56 kilogram diver jumps off the end of a 7.5 meter platform with an initial horizontal speed of 3.6 meters per second. Determine the diver's total mechanical energy at the end of the platform relative to the platform, or relative to the surface water below. Okay, so let's work on this problem. Actually, we'll turn this on too. So we have this diver. Let's move it so we can read the whole question here. So we have this diver, and he is so his mechanical energy is equal to his Eg plus his Ek from the initial situation. That would be mgh plus 0.5 mv squared. We know the m is 56, g is 9.8, h is 7.5, plus 0.5 m, which is 56, and v, which is 3.6. So what is our initial amount of energy here? 56 times 9.8 times 7.5 plus 0.5 times 56 times 3.6 times 3.6. We have 4,478. That's going to round to two significant digits, because if we look at the first given is 56, so that's two significant digits. So we would write 4500 joules. 4,500 is the initial mechanical energy. Next part of this question says, apply the law of conservation of energy to determine the diver's speed when they're 2.8 meters above the water. Well, we'll have to use this value, and I'm going to write down here the exact just before we get to that. So in this case, to find out their velocity, we know that in 3b, their EM equals Eg plus Ek again. The EM is equal to what we have here, But let's break this up and find out what we need to solve for. mgh, we know the m, the g, and the h. 0.5 mv squared. We need to solve for that v. So let's multiply everything by 2 and divide everything by m to start. So we have 2em over m equals 2gh plus v squared. Let's then write the v squared by itself. That would be 2em over m minus 2gh. And we're now going to continue this over here. So v is equal to the square root of 2em over m minus 2gh. So em I'm going to write in as accurate as I can. Over m, which is 56, minus 2g h. H is 2.8. So I have this value already in my calculator. Notice how I didn't clear it out. I'm going to then multiply this by 2, divide by 56, and then subtract 2 times 9.8 times 2.8, hit equals. This is my value that needs to be square rooted, so I square root that, and I get a v of 10 meters per second. That's my final calculation. And we'll turn this part off. So for part C, it says repeat B to find the maximum speed of the diver upon reaching the water. Well, that's actually a bit of an easier question. So let's do 3C over here. What I know is that this equation is still valid, so I can rewrite that. Square root of 2 em over m minus 2gh. However, because h is 0, I can remove that entire term and rewrite this as the square root of 2 em over m. So v equals the square root of 2, 4478.88 over 56. So let's put that in our calculator. So we have 2 times 4478.88 divided by 56. I find the square root. I get 12.6, but rounding for significant digits gives me 13 meters per second. And that's our solution. Here's another question. It says we have a 0.2 kilogram ball that's thrown straight up from the edge of a 30 meter tall building at a velocity of 22 meters per second. The ball moves up to the maximum height and then falls to the ground at the base of the building. Use the law of conservation of energy to answer the following questions, assuming the reference level for the gravitational potential energy is ground level. So what is the total energy of the ball at the start when it had a velocity of 22 meters per second? So let's look at the next part of this question. It says what's the velocity of the ball at the maximum height, and what's the maximum height of the ball? And then lastly, what is the velocity of the ball when it hits the ground? So those are a number of different things we have to answer. I think that we get to number 5. So we need the velocity when it hits the ground, the maximum height of the ball, the velocity of the ball at the maximum height, and what is the total energy of the ball at the start. Okay, so let's turn on our camera. Okay, here, what we're first being asked to solve for, the total energy of the ball, so ET, is equal to, or I guess you could say EM, is equal to its EG plus its EK. So EG being mgh, EK being 0.5 mv squared. We have everything we need to solve this, so it's really just a substitution and solve. M being 0.20, G is 9.8, H is 30.0 plus 0.5, 0.20, and the V initial is 22. So with all of that, 0.2 times 9.8 times 30 plus 0.5 times 0.2 times 22 squared. So we have 107.2 joules. And that would round to 110. So ET equals 107.2, but my reported answer is 110 joules. So this is kind of the proper way to show your calculations. First we show a non-rounded solution, and then we show our reported solution. Next, let's move over to the side here and do 4b, because 4b asks the velocity of the ball at maximum height. So the ball is thrown straight up. The ball moves up to the maximum height and then it falls to down to the ground. Well, this is a bit interesting because its maximum height means that the ball is slowing down, it stops, and then it starts to go down again. So for 4b, V, I guess it should say V at max height. V at max H, or H max, is 0 meters per second. Because it can't be moving when it reaches its maximum height. So in this case, and in all cases, when you hit the maximum height of something being thrown directly up, it's going to stop before it changes direction and starts going down. So what is the maximum height of the ball? Well, in that case, we know the total energy. We've calculated that. What we need to calculate now is what is our maximum height? And we also know that our ET equals EG plus EK. So ET equals mgh plus 0.5 mv squared. Well, if my v is 0, then this whole term goes away, and I basically need to solve this equation for h. So h is equal to ET over mg, and let me move it up here. H equals, so not 110, but 107.2, because I'm going to use the most accurate solution there, over 0.20, which is my, my mass, over 9.8. So back to my calculator. This value divided by 0.2 divided by 9.8 gets me to 54.69. So I write H equals 54.69, and I'll round to one decimal point here, 4. But my reported solution is 55 meters. Okay, now let's go to the last problem. It says, what is the velocity of the ball when it hits the ground? So in order to find this, what we'll need to do is we need to so 4D, we know that ET equals EG plus EK. At maximum height, this is gone, or sorry, at just before it's the ground, this becomes a zero term. So we have ET equals EK only. ET equals 0.5 mv squared. V equals 2EK over m, and we square root that. So V is going to equal the square root of 2107.2 over 0.2. And let's determine that. We have 2 times 107.2 divided by 0.2. And I find the square root. I get 32.741. And my V rounds to 33 meters per second. That's my solution. Okay, another question. It says, many roller coasters have loops where carts roll on a track that curves sharply up into the air. In the roller coaster shown, the cart must have a minimum speed of 10 meters per second at the top of the loop to make it around safely. Assuming the roller coaster starts from rest at the top of the first hill and there is no friction on the roller coaster, what is the maximum height of the first hill in order to ensure success? So in this case here, we see that we have to hit a height of 16 with our loop, but it says as well it has to have a minimum speed of 10 meters per second at the top of that loop. So we can find out what our energy needs to be at that point. So let's do that here. So for 5, we need to have our ET equaling our EG plus our EK. So our ET has to be equal to I'll write down everything here, 0.5 mv squared plus mgh. And this is at the top of the loop. 0.5 m is, do we have m? I don't think we do. So we're going to have to do this a bit of a different way. So we don't have our mass. So the question is, can we solve this without our mass? Well, we're going to have to do some algebra to figure it out. What we're really interested in is we know our V and we know our H. So we need to write this ET in terms of m. So it is, I'm going to factor out the m, 0.5 v squared plus gh. That's what our energy needs to be at the top of the loop. Now our H max, that's where the cart is stopped at the top of the loop. So, because it says assuming the cart starts from rest, I think assuming that the roller coaster starts at rest. So that means that its energy at the top must be completely equal to g. So here we can say that ET has to equal EG, and I have my ET here. It's m 0.5. I'm going to call this VF squared plus GHF, and that has to equal mghi. So now my m can divide out on both sides. So I'm left with 0.5 VF squared plus GHF equals GHI. And I need to find the HI. So my HI equals everything here divided by G. 0.5 VF squared over G plus HF. So let's work out this. HI equals 0.5 10 squared over 9.8 plus HF, which is 16. So let's work out that on the calculator. 0.5, I have to turn the calculator on, times 10 squared divided by 9.8 plus 16. We're left with 21.1 or 21 meters. That is our solution to that problem.